Okay, hello everyone. I wanted to do a video on the complex conjugate roots case because I knew it would take up a lot of class time. And it's not too bad. Some algebra, some trig stuff you may have to remember, but it's actually not too bad. All right, so, and I don't know if anyone's taking complex variables or complex analysis, but that might come. You might see something in a minute when we do, when we evaluate the expressions. Okay, so we do the quadratic formula, right? And I wrote it down to save time, so you may want to pause the video, write everything down, and come back and then take notes on it, okay? And so we set up our characteristic equation here, or our auxiliary equation, I think is what your book calls it. And we have to do quadratic formula. So A is 2, B is -3, C is 4. And we get some complex solutions because the discriminant will be negative, right? -23. And so we have 3/4 plus or minus the square root of 23 divided by 4i. Okay. So what we're going to have to use is actually Euler's formula, which says e to the I theta equals cosine theta plus I sine theta. We're also going to use the fact that cosine of negative theta, cosine is an even function, so that means cosine of negative theta will just give you back out cosine theta, and sine is an odd function, so that means sine of negative theta equals negative sine theta. This is actually the even and odd functions, that's something from pre-calc, but you may need to use that. Okay, so again, you might want to pause the video and write this down. Hopefully you can read my work. All right, so let's see if we can follow my steps that I wrote out. All right, so the first thing, once we get our two solutions, right, y sub 1, y sub 2, we know the general solution is c sub 1 e to that, right? So it's, I don't know if you can see that. Remember, our general solution is c sub 1 e to the mx, right, plus c sub 2 e to the, let's say, m1, m2x, right, something along those lines. All right, and now remembering properties of exponents, this is really, you don't have to write this out. Just I want you to make sure you're clear on how I went from one step to the other. But this is really e to the 3/4 x times e to the square root of 23 over 4 ix, right? That's just properties of exponent. And so what I did, then I factored out an e to the 3/4 x, because that's going to be in both terms, right? Because 3/4 is here and 3/4 is there. And in the first term, I'm going to be left with c1 times e to the imaginary part, right? Square root of 23 over 4 ix. And then c2 is e to the -23 ix. All right, and we're going to use this property here that tells us e to the I theta is cosine theta plus I sine theta to rewrite this part in here. Okay, so the e to the 3/4 x will stay on the outside, and then we have c1 times, well, just following this formula. Okay, this is, I'm not in my notability, which is nicer than Docerius lets me create videos, so let me stop complaining. All right, so from there, we are just substituting in this e to the I theta, right? And so if you want to look at this, I guess I could have put, I could have moved the I to the side, I guess to the front, right? So to the front, and then everything else is sort of grouped with the theta, right? So you see, it's just, that's how it's translated here. So it's c1 times cosine of square root of 23/4 x plus I sine of square root of 23/4 x, right? So this all corresponds to this first part here, and then this right here just corresponds to that. Okay, so I'm just using Euler's formula, replacing that in, okay? All right. So again, you can pause the video to look to see what's going on. Okay, so I actually added an extra line because I had forgot a line, so I added an extra line, but we left off looking at the conversion Yeah, I think it's called convert. Yeah, from converting from just the imaginary to Euler's formula. And now for this part here, so I added this extra line. So if you wrote down stuff before, you didn't see that extra line, but I added this extra line because I wanted you to see how for this new line here, it's different because I'm using the fact that cosine function is even and sine function is odd. And so I wanted to take that negative outside of, the negative outside of the function. And so to do that, now this is just cosine of whatever's in the inside minus odd sine of that. Okay, so that's what I did there. I just used that property, those two properties. Okay. All right, so now we can factor it even further. And how did I factor it? I put just the imaginary parts together. You know, that's what we usually do with complex numbers, right? So I put the real part together and then put the imaginary part together. And what I'm doing is C1 plus C2. So I made that lowercase, and I'm going to combine that together to make it a capital C sub 1, all right, and a capital C sub 2. If you want, you know, you can change the variables. I wouldn't use D, though, because remember that sort of represents a differential operator. But you can use maybe P1 and P2 or something like that. You can change the constants if you can't tell the difference between lowercase and uppercase in your C's. All right, and so now we have... right, so I just rewrote it as capital C sub 1 times cosine plus this, and that's our solution. And so thus what that tells us is that when we have complex conjugate as our roots, the real and imaginary parts are both, let me change back to yellow. The real and the imaginary parts are both individual solutions to the differential equations. And so therefore, y sub 1 is just e to the 3/4 x cosine the square root of 23 over 4x, and y sub 2 is e to the 3/4 x sine of square root of 23 over 4x, right? And so that was those solutions there. And so in general, to avoid what we having to go through Euler's formula all the time, we have this fact. In general, for complex solutions, it'll be just c sub 1 e to the ax cosine bx plus c sub 2 e to the ax sine bx. And a and b are represented when you do the complex conjugate. Separate those two, separate your real and your imaginary parts, and that's what a and b will be. All right, we are done with this video.